In this videocast, we'll look at acid-base titrations. In section 4.6 of your textbook, back in chapter 4, we briefly described something called titrations. In an acid-base titration, a solution containing a known concentration of base is slowly added to an acid, or the acid of a known concentration is added to the base. Acid-base indicators can be used to signal the equivalence points of a titration. The equivalence point is the point at which the stoichiometrically equivalent quantities of acid and base have been brought together. Alternatively, a pH meter can be used to monitor the progress of the reaction, producing what's called a titration curve. A pH titration curve is a graph of the pH as a function of the volume of the added titrant. The shape of the titration curve makes it possible to determine the equivalence point of the titration, and the curve can be used to select suitable indicators and to determine the Ka of a weak acid or the Kb of a weak base being titrated. If you take a look at this picture in your textbook, you'll notice that there's a beaker containing some hydrochloric acid, and then in the burette right here is some NaOH. This is a typical setup using a pH meter to monitor the pH as the titration occurs. The NaOH in the burette is called the titrant, and it's a standardized solution of known concentration. And of course, you'll figure out exactly how much volume you have because you're using a burette. The HCl solution is stirred during the titration to assure uniform composition, and so the pH meter reads the pH as you go along. The HCl would be of an unknown concentration, but you would know how much you have, the volume, to start with. Let's take a look at some calculations involving titrations, and we'll begin with a calculation of a strong acid, strong base titration. Strong acid, strong base titration. So make sure that you have your sample calculations page out, and on your sample calculations page, we're going to start with section 17.3 where it says titrations. And the first question says, calculate the pH when the following quantities of 0.1 molar NaOH solution are added to 50 milliliters of 0.1 molar HCl. And you start at 49 milliliters, then we'll look at 50, and we'll also look at 51. So the steps in doing a titration problem are number one, figure out the moles. Number one, figure out the moles of acid and base you have. When in doubt in a titration problem, always make sure that you convert to moles. Always make sure that you convert to moles. Okay, that's number one. Number two, then, write the balanced chemical equation of the acid plus the base. Write the balanced chemical equation of the acid plus the base. And then number three, go ahead and ice table it. Ice table it and figure out which thing is going to be completely used up, the acid or the base, depending on how much you have of moles of each of those. And then once you've decided what's left over at the end of the ice table right here, then you make your next move. If there's some acid left over and it has not been neutralized, then you run the calculations based on the acid left over. If there's some base left over, you run the calculations on the base. If it's a weak acid or a weak base, then it gets really fun. Here we happen to have a strong base, NaOH, and a strong acid, HCl. Okay, a strong base and a strong acid, HCl. And so that makes it so we're not going to have a weak acid or a weak base left over. So step number one, calculate the moles. So let's start with HCl. Using the molarity triangle now, we're going to look for number of moles. And find this, we'll take the number of the molarity of the solution, which is 0.1 molar, and we'll multiply it by our liters. We're told there's 50 milliliters of the HCl. If you multiply those together, that's our moles of HCl that we begin with. Okay? Second step is to find our number of moles of NaOH, and we're told in this that it's also a 0.1 molar solution. So take 0.1 molar times the amount, and if you look in letter A, we have 49 milliliters, so that's 0.049 liters. And if you multiply these two guys together now, we end up with 4.9 times 10 to the negative third moles of the NaOH that are going to be used in the titration. So that's step number one, go to moles. Always important at titration problem, go to moles. go to moles. Step number 2, write the balanced chemical equation. So now we have NaOH added to some HCl. Of course, this is a strong acid and a strong base titration, so we end up with NaCl over here, which you should recognize right now as a salt that will do nothing in solution. It will not act acidic or basic. It will be neutral because Na comes from a strong base and Cl comes from a strong acid. And we'll get some water over here that won't do anything except for just add some water. So ice table this guy. Initially, you start with 4.9 times 10 to the negative third moles of this, and 5.0 times 10 to the negative third moles of this. None of this, none of this. Now you have to look and see which one is smaller, because that's the one that's going to be used up. So there's less NaOH than HCl, so we'll lose 4.9 times 10 to the negative third of this and an equivalent amount of HCl. Lose 4.9 times 10 to the negative third, and so that at the end we end up with no NaOH left. And as far as HCl goes, we have 0.1 times 10 to the negative third moles of HCl remaining. So step number 1 was moles. Second, write the balanced equation. Third, ice table it. We've done all 3 of those steps, and now comes the decision time. What is the pH based upon? Well, of course, I didn't even write anything over here at the NaCl. I would have gained 4.9 times 10 to the negative third, but the pH isn't going to depend on the NaCl. It's not going to depend on the water. It's not going to depend on the NaOH because there's none of that left. What is the only thing the pH is going to depend on? Well, it's going to depend on my moles, or my amount of HCl that's left. HCl happens to be a strong acid, and if you want to find out the pH of a strong acid solution, you simply take the negative logarithm of the H plus ion concentration. And of course, since it's a strong acid, it will completely dissociate, and this right here is your number of moles of H plus that will be in solution. So to find the H plus ion concentration, though, you have to go back to the molarity triangle and take your moles that you have and divide it by your total number of liters. Notice our number of liters has changed because we add 49 milliliters of base to 50 milliliters of acid. So 49 plus 50 gives me 99 milliliters. So my concentration will be 0.1 times 10 to the negative third moles divided by my liters, which is 99 milliliters, or 0.099 liters. Divide those 2 critters, and I end up with 1 times 10 to the negative third for my concentration of H plus. And of course, if you take the negative log of that, which you can probably do in your head, you know that your pH is going to end up being 3. So now let's take a look at when we have 50 milliliters of NaOH added to the 50 milliliters of the 0.1 molar HCl. Notice they're both 0.1 molar. Well, if we follow our normal steps, we calculate the moles of each. And if you remember from the first problem, when you have 50 milliliters of 0.1 molar, the moles of HCl were equal to 5 times 10 to the negative third. And if we find the moles of NaOH, NaOH now will be the 0.05 liters times our concentration, which is 0.1 molar. Multiply those 2 critters together, and of course you end up with 5 times 10 to the negative third moles of NaOH. So we have equal number of moles of HCl and NaOH. And if you write the balanced chemical equation for these 2 guys, HCl plus NaOH, and you ice table it, you're going to start with 5 times 10 to the negative third and 5 times 10 to the negative third, and maybe you can see what's going to happen. At the end, you're going to end up with 0 of this, 0 of this, and 5 times 10 to the negative third moles of NaCl. So there's no acid and no base remaining when you have equal amounts, just the NaCl. Now it turns out that the NaCl, of course, is a salt that came from a strong base and from a strong acid. So what's it going to do in solution? Nothing, right? So the only thing affecting the pH is just pure water with NaCl dissolved in it. So what's your pH? Well, neutral. pH is equal to 7. So let's look at the last situation now when we have 51 milliliters of NaOH added to the solution. So if first step, of course, is to find the number of moles, and if we find the number of moles of this, we find out that we have 5.1 times 10 to the negative third moles of this. And if you look back, we had 5.0 times 10 to the negative third moles of HCl, and none of the products, NaCl or water. Now you have to take a look and see which one is the smallest amount. Of course, that's the one that's going to be used up. So we'll lose 5 times 10 to the negative third, and we end up with none of the HCl. We'll lose 5 times 10 to the negative third, and we end up with 0.1 times 10 to the negative third moles of the NaOH remaining in solution. So we'll also gain 5 times 10 to the negative third moles of the NaCl, but of course we know that NaCl is not going to affect the pH at all. So what's going to happen to you? And what's going to happen to your solution? It's going to be driven by the strong base that's in there. And if you want to find the pH of that, first you have to find the concentration. So take 0.1, whoops, I wrote it as 0.01, sorry. 0.1 times 10 to the negative third moles and divide it by your total number of liters. Now remember, you added 51 milliliters here to 50 milliliters of this, so 101 milliliters. So 0.1 times 10 to the negative third divided by 0.101 liters. Divide those two and you'll get your concentration of approximately 1 times 10 to the negative third. That's the approximate concentration or molarity now. After you divide those two, notice it'd be a little bit different, but not much. And then, of course, to find the pH of that, it's probably best to take the negative log of it first to give you the pOH. And so the pOH of this turns out to be about 3. Subtract that from 14, and then it ends up being that your pH is equal to 11. So far we've only looked at titrations with strong acids and strong bases. Now let's take a look at a titration where we have a strong base, NaOH, added to a weak acid, HC2H3O2. So this is a strong base added to a weak acid. This adds a unique twist to our titrations. So it says calculate the pH when the following quantities of 0.1 molar NaOH solution are added to 50 milliliters of 0.1 molar acetic acid. Look up the Ka. So we're told that we have 45 milliliters of NaOH added. We still follow our same 3 steps. Step number 1, remember, is to find the moles. Step number 1 is to find the moles of each. And to find the moles, remember, use molarity is equal to moles divided by liter triangle. So to find the moles, moles are equal to our molarity. In the case of NaOH, it's 0.1 times our liters, which is 0.045 liters. So our moles of NaOH are 0.0045 moles of NaOH. That's our start. Okay, and then the second thing we need to do is we need to find our moles of acetic acid, and acetic acid is 0.1 molar as well, and we need to multiply that by our 50 milliliters, and milliliters are 0.050 liters. Multiply those two together and you end up with 0.0050 moles of HCl. So 0.0045 NaOH, why did I say HCl? I'm totally wrong. HC2H3O2, that's our weak acid. Weak acid right up here. Okay, so this is our number of moles of both, and that's always step number 1 is go to moles. Go to moles. Step number 2 now is to write the balanced chemical equation for the reaction between the two. Write the balanced chemical equation for the reaction between the two. So we'll take our NaOH, and we'll react it with our acetic acid, HC2H3O2, and we'll get our products of sodium acetate, which is going to be very soluble, so I'll write it as Na plus and C2H3O2 minus, and we'll get some water. And then step number 3, ice table it. Make sure you ice table it with the moles. So we're told that we have 0.0045 moles of this and 0.0050 moles of this. None of these things to start with. Now look at which one's the smallest, and of course the smallest one is the one that's going to be used up. So we'll lose 0.0045, end up with none here. We'll lose 0.0045 here. We'll gain 0.0045 here, gain 0.0045 here, and of course water we're not going to be concerned about. And so we end up with 0.0005 moles of this critter. This one we end up with 0.0045 and 0.0045 over here of this guy. We don't worry about that. Now, once you've ice tabled it, remember it's decision time, and it's to decide what thing is going to affect the pH. Obviously, NaOH is not, because it's all gone. There is some acetic acid left. Let's look at that. There also is some NaOH that is, some Na plus that has been produced, but if you remember back from chapter 16, ions that come from a strong base or ions that come from a strong acid do nothing in solution, so that's not going to bother us at all. But we do have this C2H3O2 minus ion here, and that ion, remember, is the conjugate base of this weak acid, and a base, conjugate base, acid pair form a special solution. This solution is called a, you got it, buffer. And how do you find the pH of a buffer solution? Well, the easiest way is to use the Henry-Hasselbalch equation, where pH is equal to pKa plus the log of base over acid. So you can find it directly using the Henry-Hasselbalch equation. Now, if you look up the Ka in the back of the book for acetic acid, the Ka is equal to 1.8 times 10 to the negative fifth, and if you take the negative log of that, the pKa is equal to 4.76. And so you can plug in 4.76 plus the log of the base, of which we have a lot of, 0.0045, divided by the acid, of which we don't have a whole lot, 0.0005. And remember, this is in moles, but I'm supposed to divide it by my number of liters because it's supposed to be concentrations in this. But remember, I've added the two together, and so 45 plus 50 gives me 95 milliliters, or 0.095 if I could fit it in there, 0.095 liters here. What's going to happen to those volume amounts in this equation? Well, the 0.095s are going to cancel, and so you can directly calculate the pH using the Henry-Hasselbalch equation without taking your moles and converting it to concentrations. Plunk this into your calculator to get the pH. We get 0.0045 divided by 0.0005 as being 9. Log of 9 is pretty close to 1, so you add 1 plus 4.76, and you end up with about 5.7 for the pH of your solution at that point. Now, the second part of this problem is when you have equal amounts of base and the weak acid. And we'll work this problem too, but it helps already that we have the moles of the acetic acid. So, take your NaOH, react it with the acetic acid, get your Na plus and C2H3O2 minus, and go ahead and separate them because they're going to be very soluble in water. Get your water, write your ice table, initial change end. And initially we have, calculate the number of moles now, 0.005 moles of both of these. None of this and none of this. In the end, of course, we're going to end up with none of this, and 0.005 moles of this and 0.005 moles of this. So you come to decision time again. what thing is going to affect the pH. Well, there's no NaOH left, there's no acetic acid left, but there is some of this critter remaining, and there's some Na+. Of course, if you remember, Na+ comes from a strong acid, so it's going to do nothing. But it's from a strong base, I'm sorry. But the C2H3O2- comes from a weak acid, and so it will act as the conjugate base, and this will act basic in solution. Well, how do you figure out the pH of a weak base? You might not like this very much, but what we need to do now is take our weak base, C2H3O2-, react it with water, and make an ice table to find out what the OH- ion concentration is going to be in the solution, because once we find the OH- ion concentration, we can take the negative log of that and find out what the pH is going to be. So we know that it's going to turn out to be basic because of this anion right here, and we write an ice table for it. And what we need to do then is put in the initial concentration of this, but notice we did this calculation in terms of moles, so we have 0.005 moles. So to find the concentration then, we can take and use the molarity triangle. Molarity is equal to moles divided by liters. We have 0.005 moles of the C2H3O2. And notice what we have is in terms of amount of solution now. Remember up here at the top of the problem, it told us that we added 50 milliliters of this to 50 milliliters of the acid. So we have a total of 100 milliliters. So going back to this calculation now, 100 milliliters is 0.1 liters. Divide those. My concentration is 0.05 molar. Now, I can go ahead and fill in the ice table down here. The ice table is 0.05 molar to start with. None of this, none of this, none of this to start with, because all of this, of course, was used up here in this titration, but a little bit of this is going to react with water. So I will lose X, don't worry about, gain X, end up with X here, and 0.05 minus X. After I've written the ice table, now I can set this equal to the Kb of C2H3O2-. Remember, it's acting as a base. So I can write X squared divided by 0.05 minus X is equal to the Kb of C2H3O2- ion. Now I can take a look in the back of the book, but I'm not going to find C2H3O2 in a list or a table of Kb's. But what I will find is I'll find the Ka of acetic acid, HC2H3O2. And if I keep in mind that Ka times Kb is equal to 1 times 10 to the negative 14th, I can solve for one if I know the other. In the back of the book, I'll find that Ka is 1.8 times 10 to the negative 5th. This times Kb is equal to 1 times 10 to the negative 14th. Divide both sides by 1 times 10 to the negative 5th, or I'm sorry, 1.8 times 10 to the negative 5th. These cancel. Now I get my Kb, if I punch this into my calculator, is equal to 5.56 times 10 to the negative 10th. I can now put this into my calculation right here, and I'll slide this paper up just a little bit. Notice I'm putting it in for Kb now, because that's my Kb of the C2H3O2-, the conjugate base of acetic acid. So I've got X squared is equal to 5.56 e to the negative 10th. forget the negative sign there. And then this is divided by 0.05 minus x. I'm going to ignore this x and say it's small compared to 0.05. Multiply both sides of the equation by 0.05. That gets rid of this here. Square root both sides, and I end up with x equaling 5.27 times 10 to the negative 6th. Try that on your calculator if you're not sure. This, of course, is equal to x, and if I look at my ice table, what is x? Remember, x is my OH minus ion concentration, and to find the POH, then I just take the negative log of that number. So take the negative log of 5.27 times 10 to the negative 6th, and I get approximately 5.28 or so. That's equal to my POH, and to find the pH, then I subtract it from 14, and then I get a pH of approximately 8.72, which makes sense because the solution is slightly basic, just a little bit basic, remember, because of this anion right here being present at the equivalence point where both my moles of acid, my weak acid, and my strong base are equal to each other. So the last part of this problem is letter C, and now it says calculate the pH when there's 0.1 molar NaOH and 50 milliliters once again of my acetic acid, and this time I have 51 milliliters of NaOH. 51 milliliters of NaOH. So first step in this is to write the chemical equation of the NaOH and the acetic acid. So let's start with that. NaOH and acetic acid. This is part C of the problem now. And this is going to react, of course, to give us some C2H3O2 minus, some Na ion, and some water. And the water is going to do nothing in the solution. The Na will do nothing in the solution. And of course we have none of this to start with. And if I ice table this, the first thing I want to do is find out how many moles of NaOH I have and how many moles of HC2H3O2 I have. And if I look back here at some of my other problems, my HC2H3O2, when I have 50 milliliters of it, is 0.005. So I have 0.005 moles of this stuff to start with. And then my NaOH, I'll need to figure that out, but I'm told that I have 51 milliliters of it, and if I use the molarity triangle, molarity is equal to moles divided by liters, and solve for moles, and then my moles will be equal to my molarity. My molarity, remember, is 0.1 times my liters, which is 0.015, which means I have 0.0051 moles of the NaOH. Now I need to look at these two and decide which one's going to be used up, and of course the smaller one will be used up, so I'll use up 0.005 moles of this, and I'll end up with none. I'll gain 0.005 moles of this stuff, so I'll end up with 0.005 of this conjugate base right here. I will lose 0.005 here, and I'll end up with 0.0001 moles of NaOH left, and also 0.005 moles of C2H3O2 minus. So once I've done that, I need to decide what thing is driving the pH or causing the pH in here, and it's not going to be the Na, because that, of course, is just the portion of a strong base that's going to do nothing in solution. It's not going to be water, so and there isn't any acetic acid left, so it's going to be one of these two things that drives the pH. And if you take a close look at them and ask yourself, what kind of things are these? NaOH, you know, is a strong base that completely dissociates in water. C2H3O2 is a weak base. and it will partially dissociate in water, just a little bit. And if you look, the concentrations, I know that the NaOH is about a little bit less than the C2H3O2, but remember this is strong, and so you're going to get a complete dissociation. So if you have a choice here, always choose the strong thing for driving the pH. And if you're not sure, you can go ahead and set up an equilibria with the weak base, but you'll find out that there's an awful lot of OH minus already in the solution that kind of drowns everything else out. So as long as there's some of the strong electrolyte left in there, just assume that that's the thing that drives the pH. So from here, what we can do is we can find the molarity for this. Molarity, remember, is equal to moles divided by liters. So my moles are 0.0001 divided by my liters. Now I've had 51 milliliters of NaOH and 50 milliliters of C2H3O2, so I have 101 liters. So divided by 0.101, so 0.0001 divided by 0.101. It turns out that's 9.9 times 10 to the negative fourth, and take the negative logarithm of that to find the POH, because remember that is the OH minus ion concentration, and so you end up with a POH equaling 3.00 approximately, pretty darn close to that. 9.9 close, of course, to 1 times 10 to the negative third. Subtract that from 14, and then you end up with a pH equal to about 11. So if you end up with a titration where you have a strong substance with a weak substance, if there's strong left over, that'll drive the pH. That happened in letter C. Looking back in letter B down here, if you end up and you have neither the strong base nor the strong substance nor the weak substance left, both went away, it'll be the conjugate of the weak thing that will drive the pH. The conjugate of the weak thing. In this case, it happened to be the conjugate base of a weak acid. But if this happened to be a weak base, this would be the conjugate acid of it. And then lastly, if it turns out that there's more, this happened in letter A now, if there's more acid, weak substance than there is of the strong substance, then you're going to end up with a buffer solution, because you'll end up with some of that weak acid along with some of its conjugate base remaining, and the buffer solution can be calculated using the Henry-Hasselbalch equation.